Welcome to Presidency Senior Secondary School online class. Today, 4th June 2021. So, last two classes we have discussed about group 16 elements of P block, that is oxygen, sulfur, selenium, tellurium and polonium. So, last two lectures I have already discussed some general position or properties of group 16 elements. Today we will discuss remaining or last part of the general discussion on group 16 elements. So in our last class we have discussed hydrides of group 16 elements and structure of group 16 elements. So hydrides of group 16 elements are water, H2S, H2SC and H2T. So these are four hydrides: H2S, H2O, H2S, H2SC and H2T. So in last two classes we have discussed about other properties and our last discussion about structures of hydride. All these hydrides are sp3 hybridized and each molecule containing two lone pair and two bond pair, and their bonding angle is less than ideal tetrahedral angle of 109 degree, and here due to two lone pair bond angle is 104.5 degree, here 92.1 degree, here 91 degree, and H2T where bond angle is 90 degree. So we have already discussed about their structure. Today we will discuss about their general trends in properties. So next we will consider trends in characteristics. So first we consider volatility, that is trends in volatility. Volatility means which hydride is easily volatilized or vaporized and which one is less volatile. So volatility actually depends on amount of intermolecular forces. In case of water, since here intermolecular force is very strong due to hydrogen bonding, so here water is least volatile among them due to hydrogen bonding. Then H2T, then H2SC. So most volatile among them is H2S. Actually this one least volatile because of hydrogen bonding. Other three where hydrogen bonding is absent. So deciding intermolecular force is van der Waals force, which depends on size and mass. So among them size and mass is highest among H2T, then H2S, H2SC and least H2S. So least intermolecular force, so most volatile. So this is order of volatility. So volatility increases in this order. So volatility and boiling point are inversely related. So if this is order of volatility, then order of boiling point reverse one. So this is boiling point order. Boiling point increases in this order. So least volatile means highest boiling point. Most volatile means least boiling point. Actually, boiling point and volatility are inversely related with one another. So least volatile, so most volatile, so least boiling. So this is order of volatility and this is order of boiling point. So boiling point and volatility both depends on intermolecular forces. If intermolecular force is strong, then volatility is least, and if intermolecular force is weak, volatility is highest. So this is order of volatility, and here order of boiling point. So here highest boiling point because of strong intermolecular forces, which is hydrogen bonding, and here least boiling because of weakest intermolecular forces, that is van der Waals forces. So the highest boiling point and low volatility of water is due to hydrogen bonding So highest boiling point among hydrides of group 16 is water due to hydrogen bonding. Due to hydrogen bonding, where association of water molecule takes place. So this is highest boiling. Now hydrogen bonding is not present in other hydrides, where hydrogen bonding is absent. So here intermolecular force is van der Waals force. So van der Waals force depends on size and mass. So size and mass highest for H2T, then H2SC, and least H2O. So first we consider trends in characteristics of hydrides of group 16 in respect of volatility. So this is order of volatility, and reverse order is boiling point. Highest boiling means low volatility, least boiling means high volatility. So here high boiling water because of association due to hydrogen bonding. Here hydrogen bonding is absent, so here intermolecular force is van der Waals force. So van der Waals force depends on size and mass. So size and mass. So first we consider molecule where hydrogen bonding is present. So among them hydrogen bonding is present in water, so highest boiling. Other hydrogen bonding are absent, so deciding force or intermolecular force is van der Waals, and van der Waals force is highest for this one because of highest mass and size, then this one, then this one. So this is order of boiling point. So highest boiling because of hydrogen bonding due to association, least boiling because of low value of van der Waals forces due to smaller size and mass. So this is order of boiling point, and this is order of boiling point, and this is order of volatility. So here an important question: why water is liquid at ordinary temperature and H2S is gas? Water is liquid at ordinary temperature. This one is liquid at ordinary temperature, but this one is gas at ordinary temperature. So this can be easily explained on the basis of hydrogen bonding. So in water, central atom is oxygen, having high electronegativity and small size. So water can form hydrogen bonding. So association takes place. So water is high boiling liquid. H2S, where central atom is sulfur, larger size and electronegativity is less. So water cannot, so H2S cannot form hydrogen bonding. So this one is gas at ordinary temperature. So question is, why water is liquid? Because here central atom is oxygen, which is highly electronegative and small size. So hydrogen bonding takes place. So it is liquid at ordinary temperature. H2S, where central atom is sulfur, low electronegativity and larger in size, so it cannot form hydrogen bonding. So here association is not possible. So it is gas at ordinary temperature. So here note this question. Explain why. So here important question. Explain why water is liquid at ordinary temperature, but H2S is gas. So this is very important question. Water is liquid because of hydrogen bonding. H2S is gas, where hydrogen bonding is absent. So this is our first trends in characteristic, volatility. Next we consider second one, acidic character. So acidic character of hydrides of group 1611 follows this order. So write this question and try to write answer. Question is, explain why water is liquid at ordinary temperature but H2S is gas. Water is liquid at ordinary temperature because of hydrogen bonding where association takes place. H2S is gas because here hydrogen bonding is absent. So next we consider acidic character of hydrides of group 16. So this is order of acidic character. So most acidic is H2T and less acidic is H2O. So acidic character follows this order. So acidic character increases down the group. So this one is least acidic and this one is most acidic. So this can be easily explained on the basis of size. As we move down the group, size increases, so bond dissociation energy decreases and therefore acidic character increases. As we move down the group, acidic character increases. This one least acidic, this one most acidic. Why acidic character increases down the group? Because as we move down the group, size of the central atom increases, and as size of the central atom increases, bond dissociation energy of hydrogen and central atom decreases. So as bond dissociation energy decreases, acidic character increases. So acidic character can be explained on the basis of size of the central atom, oxygen, sulfur, selenium and tellurium. As we move down the group, size of the central atom increases, and as a result bond dissociation energy decreases, and as bond dissociation energy decreases, therefore acidic character increases down the group. So write all this. So this is very important for our exam. So which one is most acidic? H2Te. This is because size is highest of central atom, so bond dissociation energy lowest. Highest size, bond dissociation energy lowest. So write all this. This is very important for our exam. So this question is very important. Explain why H2T is more acidic than H2S. H2T is more acidic than H2S. So answer of this question is, in case of H2T, central atom is tellurium, and in case of H2S, central atom is sulfur. And we know that size of tellurium is more than size of sulfur. So as size increases, distance between central atom and hydrogen increases. Central atom and hydrogen increases. So bond becomes weaker. So it is easy to dissociate. That is, bond enthalpy is low. Easily it produces H positive ion. That is, bond enthalpy is low if size is large. And if size is small, then bond enthalpy is high. So answer of this question is, in H2T, central atom is tellurium, and in H2S, central atom is sulfur. And since size of tellurium is more than size of sulfur, so bond dissociation enthalpy of T-H bond is lower than bond dissociation energy of selenium hydrogen bond. So this bond is easily dissociated to produce H positive ion. So H2T is more acidic than H2S. Very important question. Try to write this question and answer. So our next trend is thermal stability. So thermal stability follows the order. So as we go down the group, as we go down the group, size of the central atom increases, so thermal stability decreases. So this one is thermally most stable and this one is thermally most unstable. As we go down the group, size of the central atom increases, so thermal stability decreases. Thus on going down the group, size increases and therefore thermal stability decreases. So write this. So our last trend is reducing character. So reducing character and thermal stability are inversely related. So this one most stable, thermally most stable. So this one is least reducing. So thermal stability and reducing character. Thermal stability and reducing character are inversely related. So this one thermally stable, so least reducing. This one thermally most unstable, so most reducing. Least stable, most reducing. Most stable, least reducing. So as we move down the group, thermal stability decreases, so reducing character increases. So this is all about trends of hydrides in respect of volatility and boiling point, then acidic character, then thermal stability, and finally reducing character. Reducing character and thermal stability are inversely related. So write this. So next we consider ozone, which is allotropic form of dioxygen. Actually, oxygen contains two allotropic form. One is dioxygen or O2, another is trioxygen, also known as ozone. So next we consider ozone, O3, which is present in nature also in the upper part of atmosphere, which protects us from ultraviolet light. So ozone is prepared from pure and dry oxygen. Now when silent electric discharge is passed through pure and dry cold oxygen gas, then one part of it is converted to ozone, and this reaction is endothermic. So if we pass silent electric discharge through pure and dry oxygen gas, then one part of it is converted to ozone, O3. Not entire amount is converted to ozone. One part or partial it is converted to ozone, and this reaction is highly endothermic in nature. So what is silent electric discharge? Silent electric discharge means sparkless electric discharge, because this reaction is endothermic. If sparking is produced, then backward reaction starts. So some amount of ozone is decomposed to again oxygen. So here silent electric discharge means sparkless electric discharge is passed through pure and dry cold oxygen. So one part of it is converted to ozone, and reaction is highly endothermic in nature. So ozone is prepared by passing silent electric discharge through pure, dry and cold dioxygen gas in a specially designed apparatus called ozonizer. So there are two types of ozonizer are used. Number one is called Siemens ozonizer. And number two is called Brody's ozonizer. So for preparation of ozone, O3, starting material is dioxygen. So if we pass silent electric discharge through pure, dry and cold dry oxygen gas, then one part of it is converted to ozone. That is partially converted to ozone, not 100% converted to ozone. And this reaction or forward reaction is endothermic in nature. So this reaction is carried out in atmosphere of silent electric discharge, means sparkless electric discharge. So there are two types of apparatus are used for preparation of ozone. One is called Siemens ozonizer and other is called Brody's ozonizer. So ozone is prepared by passing silent electric discharge through pure and dry cooled oxygen gas in a specially designed apparatus called ozonizer. Two types of ozonizer are used. One is called Siemens ozonizer and other is called Brody's ozonizer. What is silent electric discharge? Silent electric discharge means sparkless electric discharge because reaction is endothermic. This is called sparkless electric discharge because the forward reaction is endothermic. Next we consider chemical properties of ozone. So next we consider chemical properties of ozone. So most important chemical properties of ozone is oxidizing agent. So ozone is one of the most powerful oxidizing agent due to the with the liberation of atomic oxygen. So next we consider chemical properties of ozone. So most important chemical properties of ozone is oxidizing character of ozone. That is, ozone acts as oxidizing agent. So ozone is one of the most powerful oxidizing agent with the liberation of atomic oxygen. So ozone decomposes to O2 and O, and this O is called atomic oxygen. So here important question: why ozone is a strong oxidizing agent? Why ozone is a strong oxidizing agent? Why ozone is strong oxidizing agent? So ozone is strong oxidizing agent because ozone easily decomposes to dioxygen and atomic oxygen, and due to formation of atomic oxygen it is considered as strong oxidizing agent. So this is very important question. So write this question, and this is answer of this question. Why ozone is strong oxidizing agent? Ozone is strong, one of the most powerful oxidizing agent because of liberation of atomic oxygen. So next we consider some oxidation reaction. So first oxidation reaction is oxidation with lead sulfide. So this is common oxidation reaction. So when ozone undergo in oxidation reaction, first of all ozone decomposes to nascent oxygen or atomic oxygen. Next, PbS reacts with oxygen forming PbSO4. So here 4 oxygen, so it is multiplied by 4. So it is also multiplied by 4. So if we sum up all this reaction, then left side PbS plus 4 O3 ozone, 4 oxygen cancel out, product PbSO4 plus 4O2. So this is overall reaction. Now color of PbS is black and color of PbSO4 is white. So what happens when PbS or lead sulfide, this compound is called lead sulfide. So what happens when lead sulfide is treated with ozone? So ozone oxidizes black lead sulfide to white lead sulfate. So what is reaction? So first of all ozone decomposes to O2 and atomic oxygen, and PbS then react with atomic oxygen forming PbSO4. Since here 4 oxygen, so 4 atomic oxygen required, so this reaction is multiplied by 4. So if we sum up both this reaction, then left side contains PbS plus 4 O3, 4O cancel, PbSO4 plus 4 O2. So this is overall reaction. So when black PbS lead sulfide is allowed to react with ozone, it is converted to white PbSO4 lead sulfate. This reaction is oxidation reaction because here PbS and here PbSO4. So addition of oxygen takes place, so this reaction is called oxidation reaction. So next we consider our second reaction. Second reaction is reaction with potassium iodide. Reaction with aqueous potassium iodide. So like previous one, this is our common reaction. So ozone decomposes to O2 and atomic oxygen. Ki, potassium iodide, aqueous means contains water, reacts with atomic oxygen forming KOH plus I2 plus O2. So if we sum up with this reaction, so 2 potassium, 2 potassium, 2 hydrogen, so 2 hydrogen, 2 oxygen, so 2 oxygen. So if we sum up with this reaction, say 2 Ki plus water, this one cancel out, ozone product twice KOH plus I2 plus O2. So this is overall reaction. So what happens when ozone allowed to react with aqueous potassium iodide? So when ozone allowed to react with aqueous potassium iodide, first of all ozone decomposes to O2 and atomic oxygen, which is common reaction. Then atomic oxygen react with aqueous potassium iodide, converting it into potassium hydroxide and iodine. If we balance this reaction, 2I, then also 2I, 2K, 2K, 2 hydrogen, 2 hydrogen, 2 oxygen, so 2 oxygen. So if we sum up both this reaction, 2Ki, H2O, O3. So this is left side. Right side 2 KOH, I2 and O2, and O cancel. So this is overall reaction. So ozone oxidizes aqueous potassium iodide to iodine. Aqueous potassium iodide to iodine. So this is our second reaction. Next we consider our third reaction. Reaction with acidified ferrous sulfate. Reaction with acidified ferrous sulfate. So in all this reaction, this one is common to all of them. It is ozone decomposes to O2 and O. Then ferrous sulfate. Acidified means it contains acid. Generally, if sulfate is present, we use sulfuric acid and nascent oxygen or atomic oxygen. Converted to ferric sulfate. So this is formula of ferric sulfate and water. So if we balance this reaction, here 2 iron, 2 iron, 2 sulfate, 3 sulfate, so 3 sulfate is 2O. So this is balanced equation. So if we sum up both this reaction, then left side 2 FeSO4 plus H2SO4, O cancel out, plus ozone. So this is left side. Right side ferric sulfate plus water plus oxygen. So reaction with acidified ferrous sulfate. So ozone decomposes to O2 and O, atomic oxygen, Ferrous sulfate, which is acidified, generally sulfuric acid is used, reacts with atomic oxygen. Ferrous sulfate is converted to ferric sulfate in water. If we sum up this reaction, 2 ferrous sulfate, H2SO4, ozone. This is left side. Right side, ferric sulfate, water, NO2. So, when ozone is treated with acidified ferrous sulfate, then ferrous sulfate is converted to ferric sulfate. This is also an oxidizing property of ozone. So our next reaction is reaction with aqueous potassium ferrocyanide. So formula of potassium ferrocyanide is K4FeCN6. K4FeCN6. So common reaction is like previous 3. O3 first decomposes to O2 and atomic oxygen. Then potassium ferrocyanide. So this is our potassium ferrocyanide in aqueous condition, means water is present, and also react with atomic oxygen, forming K3FeCN6. This one is called potassium ferrocyanide. This is called potassium ferricyanide, along with KOH. So if we balance this reaction, so this is balanced form of this reaction. So if we sum up, so left side is twice K4 FeCN6 plus water plus ozone, O cancel out. Product twice K3 FeCN6 plus twice KOH. So when ozone is allowed to react with aqueous potassium ferrocyanide is converted to potassium ferricyanide. What is difference of potassium ferrocyanide and ferricyanide? Here iron in +2 state and here iron in +3 state. So increase in oxidation state means oxidation. So ozone here used as oxidizing agent because it is converted potassium ferrocyanide to potassium ferricyanide. So this is another example of oxidizing character of ozone. Next reaction number 5 is reaction with mercury. So in this case also, like previous 4 reactions, ozone decomposes to O2 and atomic oxygen, and mercury Hg reacts with O, forming mercurous oxide. So this is our mercurous oxide. So if we sum up this reaction, 2Hg plus O3, O cancel out, Hg2 plus O2. So there is a important character in this reaction. Actually, mercury does not stick on a surface, but after this reaction, mercury stick on a surface. So this reaction is actually called tailing of mercury. During the reaction, mercury loses its meniscus and starts sticking to the sides of glass. This is known as tailing of mercury. Tailing of mercury. So when mercury is allowed to react with ozone, ozone like other reaction decomposes to O2 and O, and atomic oxygen so form react with mercury forming mercurous oxide. So this is overall reaction. Now during the reaction, mercury loses its meniscus and start sticking to the surface of glass. This is known as tailing of mercury. So what is tailing of mercury? When mercury is allowed to react with ozone, it forms mercuric oxide and loses its meniscus, and the phenomenon is known as tailing of mercury. So this is all about ozone, that is preparation of ozone and oxidizing properties of ozone. Thank you.